Okay. So last time we talked about multivariate normal distribution, right? And so you would see this is like the last property that we kind of glossed over. So we talked about a bunch of properties, and I'm not going to repeat them in the interest of time, but the main one was the defined transformations of a multivariate normal random variable, or again, multivariate normal, and we saw that the marginals are normal. And then there was this property that uncorrelatedness is equivalent to independence, which is very important for us. And in your homework problem, you're going to do an example where uncorrelatedness does not imply independence. And then this is the last property that is worth remembering or knowing. So conditionals of the multivariate normal distribution are again multivariate normal. So I'm not going to spend too much time on it, but just want to know this in case you run into it later. So if you have a vector, let's say y, and you partition it into two parts, y1 and y2, and this is a multivariate normal random vector, sometimes called they're called jointly normal. Y1 and y2 are jointly normal. Then I can ask, what is the distribution of, let's say, y1? Yeah, the question.
For covariance of two less or inverse for that, isn't the covariance of an inverse?
So this is a part, like a partition.
Oh, yeah.
So p by n minus p. So this, for example, is an n-dimensional vector. So if you remember, we can partition a vector. This is like n by 1. And so y1 would be p, let's say. This would be n minus p. So each piece is a vector. And then if you partition the covariance matrix accordingly, you'd get sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. And so each piece is going to be a matrix. So sigma 2, 2 in particular would be n. So this would be n minus p by n minus p. Okay, I'm using the block partition notation. So y1 and y2 are not necessarily a scalar. And this is not a two-dimensional vector, but rather like a general n-dimensional vector we partition into two pieces. A bunch of coordinates, coordinates would be called y1, and the rest are y2. And so I can ask, what is the distribution of y1 given y2? And it turns out to be a normal. And this is not a very obvious fact, and it's a property of a normal distribution. In particular, the mean, there is a mean, and then there's a covariance. So conditional mean of y1 given y2 and the corresponding covariance. And you can see the formulas are not trivial. But once you like see them once, it becomes familiar. The particular case, in particular, for example, you can see that the mean, conditional mean of y1 depends on y2. Okay, so this shows that in general, they're dependent variables. So in particular, if the sigma 1, 2 is not 0, then there is dependence, and so the conditional distribution changes, because the mean at least changes based on y2. So if the distribution of y1 given y2 changes as you vary y2, then they're dependent. And if this happens to be 0, as we have seen, then these terms would be 0. I mean, if sigma 1, 2 is 0, then this entire thing would be 0. So this goes away, as well as this term. And you can see that the mean and covariance would be the marginal mean and covariance, so the unconditional mean and covariance of y1. So this again confirms that sigma 1, 2 being 0 is equivalent to independence, because the distribution of y1 given y2 in that case does not change as you vary y2. And this is like an alternative characterization of independence. Okay, but in general, if sigma 1, 2 is non-zero, there is a non-trivial conditional independence structure, and it's very useful in Bayesian statistics, Bayesian regression, Gaussian processes, and so on. But we're not going to spend too much time on it in this course, so I'm going to basically conclude the discussion here. So any questions about this? Multivariate normal distribution? random variables, random vectors. So if not, then we're going to move on to basically the main part of the course, which is linear models. So far we had like basically been doing the preparations or prerequisites in a sense, some extensions you might have not seen before, but now we're going to use them in analyzing linear models. So the setup, which I'm hoping that most of you have seen, is the setting that we observe, let's say, n data points. Okay, so I from 1 to n. So is the index of the sample or observation. So we observe a sample of size n, and each piece contains observations on p variables. So xi1 up to xip for observation I, and a special variable which we want to predict, which we denote as yi. Okay, so xi1 up to xip are sometimes called predictors or covariates or features, and we are going to use them to predict yi. So for each observation I, we observe these p plus 1 set of variables. And the linear model is basically this equation. We posit that yi can be written as a linear combination of these covariates plus a constant plus noise. Okay, so there's this constant which oftentimes is called intercept and plus noise. Okay. So this defines a functional relation between xi and xij basically and yi, and this is the essence of the linear model. So how many people have seen kind of this equation? Okay, good. So that's the setting. Any questions? So far, hopefully clear. Just maybe I'm going to rewrite it while you look at it. So we most often work with the vector version. So I'm going to write down yi's into a vector, like stack them into a vector. There's going to be a matrix here, which you guys are going to help me determine. And then I'm going to write beta 0, the coefficients here, beta 1, beta 2, dot, 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 beta p, and then epsilon 1, epsilon 2, up to epsilon n. So there's this y, which is now a vector in Rn. There is the beta, which is now a vector in Rp plus 1. And then there's this noise, epsilon is now a vector in Rn. And we have this matrix here, which is going to be, I'm going to call it capital X. The design matrix will be n by p plus 1. Okay. And I would like someone to help me fill it out. Maybe starting from the first row. To help you out, I'm going to write out like what is y1. y1 is like beta 0 plus beta 1 times x11 plus beta 2 times x2, sorry, x12. So I is going to be 1, so x12 plus all the way to beta p times x1p plus epsilon 1. Okay. So what will be the first row of this matrix? Yes. 1, x11, x12 up to x1p. Yes, great. So the one, like this row gets multiplied, like the inner product of this and the beta column vector would give you exactly the top equation. So you get 1 times beta 0, so you get the beta 0, and x11 times beta 1, x12 times beta 2, up to x1p times beta p. And the second row would be, I'm going to assume that you now know this, 2p, and all the way goes to like x. What will be the last row? N1, yes, N1, and then N2 all the way to NP. Okay, so that will be the design matrix. And if you look at it column-wise, let's say this column would contain the first variable. So this is like I'm going to write it as x1, sometimes with a bar or like boldface. This is predictor number 1 or feature 1. It collects the values of all samples on this particular covariate. This could be, for example, age or something like that. This could be, for example, I don't know, height. This could be blood pressure. So each one is a single variable. So this sometimes I write it as x2, this is xp. And this is the vector of all ones. So I write this as 1. And maybe boldface 1. Sometimes I put a bar underneath to make sure that this is understood as a vector. Sometimes I write it as x naught or x0. And so the columns are basically the different predictors spelled out in terms of the sample. Okay? So far, so good. Okay, so if you just write it down in compact matrix form, then we get this y is equal to x beta plus epsilon. Okay. How many people have seen this particular form? Okay. So this is the form that you usually work with, compact linear algebra or matrix form of the linear regression or linear model. And then x is the 1, and then x1, x2. This is the column kind of expansion, as I mentioned, which is very useful for us. Now, we sometimes call this as well mu. Mu would be in Rn. This is the mean vector. Right now, there's no assumption of randomness, but as we'll see, I mean, we're going to have a random model in which this would be the mean of y, in fact. So questions? I think hopefully this is so far familiar. So what I want to maybe remind you is, or like see if you remember, is what this x beta reminds you of. Yes.
It's a beta, but I think it's a weights.
Beta, I mean, beta is the coefficients, the vector coefficients. Weights of. I mean, there are some sort of weights, but you be a little bit more precise. Maybe
Your projection.
this projection is going to come up, but this x beta, you've seen it before. Yes.
I think we saw it a lot when dealing with bases, dimensions, image engine columns.
Yes, yes. So this, yeah.
Equation used to find the kernel. I guess we use that.
I mean, you're hitting like nearby, but not the actual. So this is going to be summation beta j xj. So this is in general, if you want to say what it is, it's a linear combination of the columns. It's a weighted. I mean, the weight is in the sense weighted average or a linear combination of the columns of x. And in particular, as beta varies, so this x beta, as beta varies in Rp plus 1, this will have a name. This will have all linear combinations of the columns of x. What is it? Yeah. It's the image or the column space. Okay, so this is the image. So the key like geometric fact here is that that y is equal to something which is in the image of x plus noise. Okay, yes.
Was X guaranteed before?
We're gonna get to that. At this point, no, but we're gonna get, yeah. It's a very good question and good thing to remember. So far, no, but this is gonna be a basic assumption that we're gonna make. So image of x is like a subspace. It's this, in other words, it's like the span of the columns of x. It's the set of linear combination of x. These are all the same thing. And the like a geometric view of regression is that we're modeling y as an element, in this case mu, that belongs to the image of x, capital X we observe. This particular mu we don't observe. We just know that We know x, so we know the image. We know that there is this. So we were assuming that there is this vector in the image, and then some noise, which so far we're not assuming anything that. Okay. So far, so good. So this links with the ideas that we discussed in the first few lectures, and we're going to use them in a particular projection heavily today. Okay, so this summarizes what we've discussed so far. And then, yeah, this one, the first column is the column of one. This corresponds, this is not the intercept, but corresponds to the intercept. Intercept usually beta 0. Okay, a couple of terminology. So Y is often called a response in regression. It's a particular variable, sometimes called dependent variable, which I'm not going to use because it's confusing with dependence in linear algebra, with dependence in probability. So let's call it response or target. Machine learning people will call it target. X, capital X, the columns are covariates or features or predictors if you want. So Y and X are observed. Beta is the unknown parameter that we need to estimate, and epsilon is noise. And this noise is random. So far, we're not assuming anything about randomness. So far, it's just unstructured noise. But the key fact is that it's not observed. Neither beta nor epsilon are observed. And the capital X is sometimes called the design matrix. And it's in this course, we often assume it to be fixed, deterministic. For this reason, this is called fixed design regression. And you can have random design in which you model X as random. But we're going to do the fixed version, which is very common. And then mu, which is X beta, we can call it the signal or the systematic part, whatever you want to call it. This is the key thing. So this is our model. The modeling assumption is that that piece is X beta, the signal part. Okay, and note about the big picture. So if you think about the way that we model a single observation, so here I'm using Y as a single observation. Imagine this setup that I had. Yi is equal to beta 0 xi 1, sorry, beta 0 plus beta 1 xi1 plus beta 2 xi2 up to beta p xip. Let's drop the I. I'm going to drop the i's. So this is the model that I'm looking at. I'm just looking at one observation. So basically one observation is like generic observation or population level if you want sometimes. Beta 1 x1 plus beta. These are now all scalar. Beta p xp, and this was, so this is going to be epsilon. So it used to be epsilon I when I drop I. So this is a generic observation, and this part I'm going to call f of x, and x here would be just x1, x2, up to xp. Or you could put 1 if you want, doesn't matter at this point. 1 into it as well. So y is really a function of x plus epsilon, and that function is linear. Okay, linear in the sense that it's linear in x, or to be honest, it's affine because of this. It's going to be linear in this x if I put 1 in there, or if I don't put 1 in there, it would, if I don't put 1, that it would be affine that. Okay, and then let's figure out. Okay. So then each observation, you can think of it as yi is now f of xi plus epsilon I. And then once you write it in matrix format, you get y equal x beta plus epsilon. This is at observation level, you have a function. The thing is, we often look at it as a linear function in x, but really, if you want to think about a linear model, the linearity in beta is what matters, not linearity in x. So when you say linear model, really, we care about the fact that this function is, or like this expression is linear in beta. Because I can model a relation which is non-linear in X. Let's say you have a single predictor. I can write y is beta 0 plus beta 1, x plus beta 2, x squared. This is still a linear model, but it models a quadratic function. Okay, so we can model quadratic relation between y and the predictors, or more complex relations, as long as in terms of betas, things are linear. Okay, so the linearity here in beta, and you can see if I just form, like I have multiple observations, I would get 1, 1, 1 here, and then x, let's say 1 up to xn, and then x1 squared up to xn squared. And so you get a design matrix, you get your linear model, linear in beta, then the design is just going to take care of the fact that you're dealing with a nonlinear function. Yes?
I remember how you showed mu as the signal. I know it's not the mean, but why do you use the exact same notation as mean for signal?
Because it turns out to be the mean under our stochastic model.
Oh, so it is the same as.
Yes, but so far I'm not going to assume anything about the noise. So noise in this particular one, I don't want to assume anything about it. But later this is going to have a zero mean. Like it's going to be a zero mean vector, and that's the mean would be actually mu. So there is a reason for that. Okay, yeah. So this piece here is kind of important, but I'm doing it as an aside, as you will see. I mean, I just want to make sure that you understand that the model is fairly general in terms of modeling relations between y and x. It could model things that would technically be nonlinear. So you can have like a nonlinear relation between y and a single variable, but you can write it as a multiple linear regression, or like a vector form linear regression if you do it in this way. Okay, so you get basically a design with 3 columns. Okay. It's something that at first might not be obvious, but it's still, it's a linear model because we care about the linear structuring of data. Okay. Sounds good? Okay. That was an aside. Okay, so what is the goal? The goal is to estimate beta given the observation y and x. Hopefully you all know the problem. And then the assumption that we make, the only assumption so far we're going to make is that, let's call it x1. It's an assumption about x, and I'm going to assume that x is has full column rank. So going back to your question. So the first thing to note, or like to ask you, is what do I mean by full column rank? Okay, full rank or full column rank? Yes.
That rank X is the same as the number of columns you have in X.
Yes, yes. So full rank means it has the maximum possible rank. And if you think about a matrix, the rank can be at most the minimum of the number of rows and columns because of the fact that the rank of row and column rank is the same. So if you have a tall matrix like this, the rank here, like n is bigger than or equal to p plus 1, the rank can be at most p plus 1. And if the rank is p plus 1, which is the most that it can be, it's the minimum of the two, it's called full rank. Or you can say full column rank to emphasize that the rank matches the basically the column rank. So it's full, has full column rank, but it can't have full row rank. In particular, it means that the matrix is tall. It can't be fat like this. Okay. In a matrix like this, when you have more columns than the number of rows, it can't have full column rank. Yeah, because it cannot have at most the number of rows independent columns, like at most n, and n would be less than p plus 1. Another way of saying it is that this has exactly, let's say, the number of columns independent columns, or let's say p plus 1 independent columns. Okay, the columns, sorry, linearly independent. So this set of all columns are linearly independent. Any way you want to state it, it's just it has these two pieces of information. So in particular, it means that the rank is equal to p plus 1, and p plus 1 happens to be less than or equal to n. Okay, this is the setting that we're going to work. So why are we, so columns of x are linearly independent. So this ensures, the key part is ensures that the model is identifiable. What do we mean by the model being identifiable? How many people have heard about this, their identifiability, or is that when the statisticians say a model is identifiable? What do they mean? It's a very common term that you hear from a statistician. Is the model identifiable? Yes, the model is identifiable. No, the model is not identifiable. You make the assumption to make the model identifiable. It's like something that they really, the first thing that they think about the model is whether the parameters are identifiable. Or you can say the parameter is identifiable. Here, is beta identifiable or not? What do we mean? Anyone heard about this? So what it means is basically different parameters give different kind of models for the observation. Or if you observe, like let's say, technically different probabilistic models. We're not assuming probabilistic model here, but what in this case it means is that different betas give different mu's. Okay, in particular, if there was no noise, if I observed y, I would have observed mu. And if I know that different betas will be different mu's, I can identify beta from mu. Another way of saying it is that if I solve this linear system equation, if you give me mu, I can uniquely solve for beta. There is a single beta such that x beta is equal to mu. These are all different ways of stating the same. In other words, the model is not identifiable if I can find two different betas, let's say beta not equal to beta prime, such that x beta is equal to x beta prime. So there exists beta not equal beta prime such that this holds, then the model is not identifiable. Yes.
How's this different from like a function having one input and one output? Because I know like I guess like when he says a failure, the case where it was identifiable was when like you had multiple different betas or like x.
So you're thinking probably about a one-to-one relation, not the function having a. Yes. Yeah. So what this is saying is it's equivalent to saying that this map that maps beta to x beta. Remember x, every vector, okay, every matrix you can think of it as an operator. So this map is one-to-one. Yes. 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 So you can prove, for example, that because I did it in the morning lecture, let me do the proof. Why full rank implies identifiability. Suppose that we have beta 1 not equal beta 2 such that x beta is equal to x beta prime. Then I can rearrange, I get x beta minus beta prime is equal to 0. Okay, let's call this some c. So x times c is equal to 0. Because I know the columns of x are linearly independent, I can conclude something about this c. So the linear combination of the columns of x has turned into 0. Yes. C equals 0 by linear independence of the columns. That's the full rank assumption. And C being 0 just means beta, like our beta is equal to beta prime. So you started from two potentially different beta and then concluded that they have to be equal. So if x beta is equal to x beta prime, they have to be equal. You either assume they're not equal and then get a contradiction, or just start from two generic one and prove that they're the same. So this proves that under the full rank assumption, there's really a unique beta associated to every mu. So I can really solve this back for beta. There's a one-to-one correspondence between mu and beta, or as what's pointed out. So what was your name, by the way? Sorry, I forgot. What's your name?
Christopher.
Christopher. So as Christopher pointed out, this map is one-to-one. Okay, so maps in a one-to-one fashion. So two different betas don't go to the same thing. That would be the opposite. So this map is one-to-one. Okay. So far, so good. Okay, so this is the assumption that we're going to make. So before doing that, so this is a simple example. If you do the simple linear regression, you have the yi beta 0 plus beta 1 xi plus epsilon I. You write down x will be getting y and then x1 up to xn. And then the image of x would be the linear combination of these two columns. So it's really a two-dimensional space at most. It would be exactly two-dimensional if we have the full rank assumption. So what does the full rank assumption mean in this case? What would have to happen for x to have full rank? Yes.
There's no space.
Okay, yeah, but in this case, there's a simple, like if you just look at the, or what can we say about the second column to make sure that it's full rank? Yes. Yes, at least two of the x's are not equal, or just not all the x's are equal. So if they, like at least one of them is different than the other ones, or exactly as you pointed out, if two are different, and it's not the constant multiple of this, and so they're linear independent, which is a very mild condition. If you have a lot of, and if this really covariate, which it varies a little bit among samples, then you're done. It's not really a big condition if n is much bigger than p. As you approach, like n and p approach each other, then things become a little bit tricky. Okay, so this one you'll figure out later. Okay, so how do we solve this? So how do I estimate beta? The kind of common estimate is the least squares. It's the squares estimate. There are many different ways of doing it, but the most common one that probably most of you know is this idea that perhaps originated at least as far as I know, but there might be people before Gauss, like maybe 200 or so years ago, that try to minimize, so try to find beta such that this side is close to the other side by minimizing the errors. So let's say this is the vector of errors. I have a bunch of them. So what you end up doing is, or what he ended up doing is minimize the sum of squares of the errors. So try to minimize this sum squared, which is like the norm of epsilon squared, which is really the norm of y minus x beta squared. So find beta such that the sum of the squares of the errors between y and x beta are minimized. Okay, that's kind of a very old idea before kind of even statistics was formally around. Okay, and so if you write it down, it's just in this like vector, like remember the norm is exactly this. We're trying to minimize the norm squared. Okay. Or if you think about it really, I can drop the 2 here as well, minimizing the norm squared versus the norm itself is not going to be that different. I'm going to let it be there for now. If you let it be there, things are differentiable. And we'll see later. You can differentiate. If not, there's a bit of a non-differentiable issue at the origin. That's fine. I think the main idea was exactly because this is easy to work with and you can differentiate and so on, maybe. So we want to do this, okay? We want to find beta such that this happens. I'm going to rewrite it as, because I know that this x beta is basically carving out the image. There's a one-to-one correspondence between the set of all things that can be written as x beta for some beta in Rp plus 1 and the elements of the image. I'm going to call this mu a new variable, and this optimization would be equivalent to minimizing over mu, but now restricted to the image of x. So this is the key insight. Geometric kind of insight or change of variable. So these are equivalent. Okay. And I'm going to go one step further, and I'm just going to write an argmin here because I care about the minimizer, not the minimum value. So argmin over mu in the image of x of norm of y minus mu squared. Yes.
There is squared.
Yes and no. So for this geometric picture, it doesn't matter. But if you want to, let's say, take the derivative, so this makes things differentiable. And otherwise, you have to worry a little bit about. So remember this, there's a root. So the norm has a root, and this guy is not differentiable at an origin. So you have to worry a little bit about that. It doesn't matter as much, but with the squares, it's not a problem. But as we'll see, I mean, first, let me all this mu hat. Do you remember what the argument means? What does arg mean? Yes. Yeah, mu that minimizes. So if you think of this as a function of mu, you're minimizing this function. The argument of this function is mu. So the argument that minimizes the function is the argument. The value that the function takes at the minimum is just the minimum. So I don't care about the minimum of the function, I care about the argument. And then the argument then is equal to the argument. If I drop now, I'm going to drop the square because the squaring things is monotone on if you look at the square function on the positive or non-negative reals, it's monotone. So if I maximize or minimize this versus this, it's not going to change the argument. It's going to change the value of the minimum, but whatever minimizes this is going to minimize that as well, because there's a monotone transformation. Okay, now this one is hopefully familiar to some people. What is this problem? You're looking at a vector y and measuring the distance to mu, where mu is a generic element of the image of x, and you're asking what mu minimizes this distance. Anyone remembers? Yes. Projection, yes. So finally we meet projection. So you have this image of x, right? We have y here, potentially outside this image. Image is a linear subspace, and I'm looking at all the mu's in this subspace and looking for one, which we're going to call mu hat in the subspace, such that the distance to y, which is the size of this vector, which I'm going to call e, y minus mu hat. This vector is e. I want this distance to be minimized among all possible vectors. So if there was another vector here, it would be this, and another vector would be, the distance would be that. As I vary it, one is going to be the one that minimizes this distance, and that would be the projection. So you really, you can write it as like projection of y onto image of x. It doesn't matter, like this notation is not standard. Something like this, okay? So what is the key property of projection? Geometric property. Remember. What do we know about this error?
It's orthogonal to the subspace.
Orthogonal to the subspace, yeah. So this basically is equivalent. So mu is the projection if and only if, or equivalent to the error, which is being y minus mu hat, like if this error is orthogonal to the subspace, perpendicular. Okay, and this is going to be the defining characterization, allows me to figure out what mu hat is. So geometrically, it should be clear as we have seen before. Okay, so we're projecting and we have this relation, this key relation. Okay, the error is orthogonal to the image. So maybe expand this a little bit. So image is orthogonal. So x, if you remember, I'm gonna write the first column as x naught and then x1. These are the columns. So one thing that you can argue easily is a vector is orthogonal to the image of x, which is the span of the columns, if and only if it's orthogonal to every column. So this is equivalent to saying E is perpendicular to x naught and also x1 and also x2 all the way to xp. Or if I want to be compact, I'm going to write xj, where j goes from 0 all the way to p. So why is this true? Why being orthogonal to the image is equivalent to being orthogonal to the columns? I'm going to write it again like a different way. So E transpose xj is equal to 0, j from 0, 1 to p. So you can write it as the inner product, which can be written as E transpose xj being equal to 0. So that's equivalent. Now, any linear combination, and a general element in the image is a linear combination of the columns. Okay. So if I want to say that E is orthogonal to a generic element in the image, it's going to be E transpose summation beta j xj, where j goes from 0 to p equal to 0. If this holds for any beta, then E is orthogonal to the column, but you can see it passes through and it's equivalent to just saying that. So as long as these are all 0, then this sum is going to be 0 and vice versa. I mean, if this holds for any beta, I take like beta 1 equal beta 0 equal to 1 and the rest equal to 0, and you get this one. And if you get beta 0 equal to 0, beta 1 equal to 1, and the rest 0, then you'd get this one. So there's a one-to-one correspondence between being orthogonal to a general linear combination of a bunch of vectors and being orthogonal to each individual vector. Okay, so that's the little argument there. So we have this. Yes.
Substitute says Eli.
We'll get to that. So far, it's orthogonal to the image. So what do you think it lies in?
Kernel of X transpose.
Yes, we're building towards that, but I can say it's going to be true. So this is equivalent to saying E belongs to the image of X perp, the orthogonal complement of the image, which happens to be the kernel X transpose, but I'm actually proving that. Okay. Sounds good? Yeah. Okay, so this is equivalent to saying E transpose times x0, x1, xp is equal to 0, because if you multiply out, this is really E transpose x0, E transpose x1 up to E transpose xp. And so the reason why this is true is like this is n by 1, sorry, 1 by n, this is n by 1. The dimensions match and just passes through. So this whole thing is equivalent to basically E transpose x equal to 0. Okay, so this is equivalent to saying E is orthogonal to every column of X, because of this identity that E transpose times this can be written as just move it inside and multiply every column. Okay, so this is nothing but this statement. And if I take the transpose of both sides, I get X transpose E equal to 0 transpose, but I don't keep the track of the dimension of the 0. If I transpose both sides of the equality whole, then transpose switches the order. Okay. Now, what does this mean? What does this mean? X transpose E. Well, what can we say about? By definition, E belongs to kernel of X transpose. Okay. This is the definition of the kernel. So we started with something which is orthogonal to the image. By definition, it belongs to the image perp, and we showed that this E belonging to E is a generic vector belonging to the image perp is equivalent to E being in the kernel of X transpose. So we really also proved this statement, which I promised to prove. And you can see it's not something very fancy, it's just the fact that E has to be orthogonal to every image, we write it down in matrix form and we do a transpose and get by definition of the kernel. This is the kernel of X transpose, it's a set of all vectors that are annihilated or like mapped to zero. It's exactly kind of what we got for E. Okay, so we proved this general fact that image of X perp is kernel of X transpose, and also this nice identity. We really want this. We wanted this identity. If you knew this, you could just shortcut this from this step to step. You just immediately get the X transpose E is equal to 0. But if you want to prove it, the proof is not difficult. Sounds good? It's a good exercise in symbolic manipulation. Like this is the linear algebra. So this is geometry and algebra like together. So a geometric fact translated into algebra, you can just get intuition about geometry using algebraic manipulation. So we started with this is the geometric idea. We know this, so we get this one. On this slide, I'm assuming that you know this identity, but we proved it. And so if I write it down, so X transpose Y minus mu hat is 0. That's what we got. That's E, which is also equivalent to saying X transpose Y minus now mu hat is something in the image. So it's a vector in the image by definition and can be written as X beta for some beta, which I'm going to call beta hat. Okay, so there exists a beta hat such that I can write. There exists beta hat such that mu hat is equal to X beta hat because mu hat is in the image of X. So if I rearrange, I get X transpose Y minus X transpose X beta hat, which is this factor in. Just basically do the multiplication and rearrange, I get X transpose X beta hat is equal to X transpose Y. This equation is kind of a linear system of equations that allows me to solve for beta hat. Okay. It's called normal equations. And it's just really a restatement of the fact that the error is orthogonal to the image of X, or the error, it belongs to the kernel X transpose really. Okay. So this holds regardless of whether X has full column rank or not. We haven't used that fact yet. But if X has that property under that X1 assumption, then X transpose X is invertible. This you can verify. And so this system will have a unique solution. Otherwise, this system will not have a unique solution. And this is a manifestation of non-identifiability of beta. So there could be multiple beta hat that solve this. But if the X is full rank, then X transpose X is invertible, and then there's a unique solution, which is, we can write it as beta hat is X transpose X inverse times X transpose Y. So I can invert this, multiply both sides by the inverse. But really, in practice, you just solve it using the solver. Yes.
So if the X1 assumption doesn't hold, then the equations are identifiable.
Then the equations will have multiple solutions. And so there's not a unique beta hat. What will be unique is the X beta hat will be unique. So mu hat will be unique. Geometrically, there's only one projection. This will be geometrically true. So there's going to be a unique projection, but it can be written in multiple ways as the linear combination of the columns. Okay. So there are different ways of writing it. So then there are different beta hats. So beta hat is not identifiable. And it really doesn't make sense to talk about the rest of the properties of beta hat because it's a problem. And so in practice, the low rank assumption most likely holds if p plus 1 is less than x, because usually things are random enough, but you could be close to low rank. So close to rank deficient, sometimes called rank deficient. If it's not full rank, it's rank deficient. So the rank is full, but numerically it's close to being deficient. And then it will have issues. So this problem it will be hard to solve numerically. And a little bit perturbation would change beta hat widely. And once we assume randomness, it manifests itself in high variance of beta hat. So we'll have a very high variance. So far, there's no randomness. I mean, you're in a perfect mathematical world, under full rank assumption, there's going to be a single beta hat. But in practice, numerically, it could be full rank, but close to being like one vector could be written as almost like a linear combination of the rest, and like everything like be difficult numerically to solve. Sounds good so far? So this basically is this little slide here summarizes everything we talked about and basically a lot of the ideas from lecture 1 and 2. Like a combination of linear algebra, and now it is translating into a nice way to estimate beta in linear model, which is why least the squares. So least the squares in linear model is really projection. So here's the picture. So we have y, which is the sum of these two components. So I have a mu, which is x beta for a true beta. And because it's of the form x beta, it lies in the image of x. And there's this noise, which is epsilon. So mu plus epsilon gives me y. Okay. And then neither mu nor epsilon are observed. I just observe y. And because I know the actual mu is in the image, the best I hope is that if I find the closest vector in the image, which happens to in this case be this mu hat, then I'm going to be close hopefully to mu. It's not going to be perfectly equal to mu, but it's the best I can do. And if that closest vector, if you find it, then you know that the error is going to be orthogonal to the image, and the sum of them would give me mu, sorry, me give me y, and this angle is going to be a right angle. So this error, the E, is called the residual. This is observed. This epsilon is like the actual error that we don't observe. So I hope that distinction is clear. This one you observe once you fit, and it's y minus mu hat. Mu hat is sometimes called the vector of fitted values. Epsilon is y minus the actual mu, neither of which actually, yes.
Now, I said that U hat and E are orthogonal, since like one the E is the I guess the shortest.
Mu hat and E, yes. Yeah.
Is there a case where it's not U hat is orthogonal to X? Is it possible for it to be orthogonal but not U hat?
You're still talking about mu hat, not U hat. Mu hat.
No. Is it possible? I'm asking, is it possible for normal view? Is it possible for view?
Norm of mu. So mu hat is a vector, right? So, and then mu is also a vector. E is also a vector. So what's your question now? So mu can be, or mu is in the image, and E is going to be always orthogonal to the image, and always going to be orthogonal to mu hat and mu and anything in the image. There's always the case. Is there anything else?
Or orthogonal enough to say you found mu.
Orthogonal enough. It's just you either are orthogonal or not. So E being orthogonal to mu hat is not enough. E has to be orthogonal to the image. Okay, so if you find a vector, this may be a good question. So if you find a vector such that the residual is only orthogonal to mu hat, that's not enough. Okay, it has to be orthogonal to all the image. Otherwise, that's not going to be a projection. Okay. Yes.
So following from that, so mu hat can be part of the subspace, but E can be orthogonal to mu hat, but not orthogonal to the subspace.
Potentially, yes. Yes. I mean, you could imagine in this picture, for example, this vector, I mean, any vector that you pick, there is a plane that passes through y and that vector. And if you extend that vector enough, then you can just project onto that line. Okay, so pick any, and I'll let you figure out yourself. So pick any vector and you extend it to a line. So this is going to be a subspace of the image. And this y will have a projection onto that line, like any other projection. And if you do that projection, it's going to be, whatever you get is going to be orthogonal to the entire line and that vector in particular, but not necessarily projection onto the image. Okay. There is a particular direction that if you project onto that, it would match. It's a very good exercise, actually. So there are many different projections onto lines that lie in this image. Only one of them is the projection onto the actual image. And if you happen to like know this direction of the mu hat, and if you project onto that line, it matches. Otherwise, you only be like orthogonal to that direction. Okay. So there's a lot of things that if you contemplate this image could come to your mind, and then you could just try to answer. This is one question, for example. E being orthogonal to mu hat is not enough. There are many cases you could construct here that happens, in particular with 1D projections that do not necessarily give you projection to the whole. The other thing someone asked in the good thing about the image is that a lot of things you can visualize here. So the length of epsilon here is bigger visually than the length of E, if you do it correctly. Someone asked if this is true always. Is this true that the length of the error, the epsilon, is always bigger than the length of E? I'll let you think about it. I mean, it's a good question. Think about it offline. Maybe you can ask it on an exam later. Yeah. So it's a good question. So now the residual vector is E again, y minus mu hat is y minus x beta hat. And then the vector of fitted values is mu hat. And from this kind of geometric picture, I get a lot of identities for free. So E is orthogonal to the image. And the image is spanned by the columns of X. And so if the X has a column of all ones, let's say, which means that the model has intercept in it. Remember, if I include an intercept, usually, which we usually do, then we'll have columns of all one in the X. Then E would be orthogonal to 1, the columns of all 1. And if you expand it as an inner product, it just means that the sum of the elements of the residual vector is 0. So this is a consequence of this geometric fact. Moreover, E is going to be orthogonal to every column, which we already used actually in the process of proving or driving the result. And if you just expand it, it would mean this summation of EIX ij over j. So over I is 0 for all j. Residuals basically, you can say, are uncorrelated from the predictors. This is not random, but this is like sample correlation in a sense. It's not, this you can say that the residuals are kind of empirically zero mean, but there's no, I just don't want to say it because these are deterministic facts. They're not random facts, but let's say they sum to 0 and then they're, in this sense, are correlated, like deterministically uncorrelated, not stochastically. And then E is orthogonal to mu hat, as we discussed. So this gives you another equation between the residual and the mu hat. And what else do we get? We get this fact that So S beta is, I don't think I introduced it. Let's say this is the sum of a squares function. So as a function of beta, norm of y minus x beta squared, let's call this S beta. So beta hat is the argmin, the beta hat that we got, which was like x transpose x inverse x transpose y is, this is the argmin over beta, and the minimum value itself, which happens to be like y minus x beta hat squared, this is really the residual sum of squares. Okay, so really the minimum of S beta is the residual sum of squares. Okay, and it's just another fact. Sometimes called RSS or SSE in the book. Sum of squares of errors or residual sum of squares, RSF, is the minimum value of that cost function. Okay, so far so good. So none of these require like remembering. You just have to understand like what we discussed, the orthogonality, all of these facts would follow. A particular thing, for example, which I often ask in exams is like whether this is always true or not. And whether it's true, it depends on whether you have one in the design matrix. And you have one in the design matrix if you have intercept in the model. So you don't have to necessarily include their intercept. So for example, like you have like a model which is like beta 1 x1 xi1 plus beta 2 xi2. This is a model that passes through the origin. There's no intercept. And so when I write down the design matrix, there is no 1 in it. So there's no reason why this is true. But if I have the intercept, I have included a vector of 1s, then once I fit the regression, it has to be orthogonal. Okay, this in particular depends on whether you have the intercept in the model or not. It should be clear from the geometric picture. Okay, only the residual has to be only like orthogonal to the columns of x. If there's no columns of 1, then there's no reason why this has to be true. And then the rest should follow. Yes.
This would be true if the element values of the vector E were just not the same.
In what case? Are you talking about the intercept, having the intercept or not?
So E would be orthogonal to the intercept if the values for E in the vector of E would not all be the same.
First, we shouldn't say it's orthogonal to the intercept. It's either orthogonal to the vector of 1s or not, right? And whether it's orthogonal to 1s or not doesn't mean that all of them are the same or not. So this yeah. So if it's in the span of the vector of 1, it would mean that all of them are the same. Here you're saying it's orthogonal, right? Which means that the sum of the elements is 0 or not, right? So important difference, right? Okay. Yeah, okay, good. Any other questions? Okay, I still think I thought I had covered most of the things, but we have one more thing to discuss, a clear thing. There's an algebraic verification of this fact. So if you didn't know about projections, you could just write down this cost function and just use calculus. Yes, I have a function, multivariate function of beta. I want to minimize it. How do you minimize the function? Differentiable function. Yes.
Take the derivative under 0.
Yes, so take the derivative, set it equal to 0. That's the usual thing that people do. So if you take the derivative with respect to beta k, a generic element of beta, I let you figure it out. It's just write it down. And it would look like this. And if I collect these derivatives, so partial of s with respect to partial of beta 1, so it's a multivariate function. We have to take partial derivative with respect to all the coordinates, so beta 0 all the way to beta p. I put them in a vector, this would be a gradient. So setting all these derivatives to 0 is equivalent to setting the gradient equal to 0. Okay, and so beta hat is a minimizer minimizer implies that gradient of S beta hat is 0. This is called first order optimality condition. It's a necessary condition. It's not sufficient. And what it means is that if beta is a minimizer, this holds, but if this holds, does not necessarily mean that beta hat is a minimizer. But suppose that beta hat is a minimizer, we get this, and then you can look at this. This is the compact form of it. I'll let you figure out the details for yourself. Take the derivative and just rewrite this in this matrix fashion. So this just tells me negative 2x transpose y minus x beta hat is 0, which is really, this is like E. So this is really saying x transpose E is equal to 0. So we get that equation that we wanted, or the normal equations if you just multiply out. Ignore this 2 because those two sides are 0, you get x transpose x. Beta is x transpose y. So you get the normal equations or this residual kind of fact. The same geometric fact or the normal equations follow from setting the derivative to 0. And then you just have to argue alternative from alternative methods that this is really a minimizer. Because these are called a stationary, like a first order optimality condition holds for any stationary point. And like if something satisfies this, could be a minimizer, could be a maximizer, could be a local minima, could be local maxima, global minima, global maxima, a saddle point. All of them satisfy this. You just have to argue. In this case, this is a convex function. It has like global minima and local minima are the same, and because it's convex, it has a minimum, not a maximum. And you can verify it, in fact, via the second order derivative, which is a Hessian. So the Hessian of this cost function would be just x transpose x. And if the Hessian is positive semi-definite, which happens in this case, then it's a convex function. It's like ball shaped like this, and it would have a minimum. If the Hessian is negative semi-definite, then it will have a maximum. Yes, hence we have a minimum. So these are facts from optimization. I'm not going to dwell too much on it, but if you're interested, you're welcome to try it. This gives you a very, let's say, brute force calculus way or algebraic way of calculating, but using the same geometric kind of idea without actually realizing it first. Okay, so you get the same thing. And so the idea is that gradient being 0 is exactly the same as E being orthogonal to the image or being inside the kernel of X transpose. So really algebraic and geometric views kind of match. So the first order optimality conditions from the optimization perspective is giving you the orthogonality principle from the geometric perspective. So the nice thing about math is kind of, if you do it right, everything kind of matches. You don't get into any questions about this. I have a very quick one last slide, which is, so now if you do it on the linear regression, sorry, the simple linear regression, you have p equal 1, the example that we did, you just have one column of all ones and then just one covariate. You calculate the x transpose, it looks like this. You calculate x transpose y, it looks like this. You calculate the beta hat via that formula, x transpose x inverse x transpose y, you get, after some manipulation, you get these formulas. I'll let you do this. These are the formulas that you've seen probably 100A and or B or some other course 101. And it's just, all of them come from the fact that you're projecting y onto the image. You can like directly project y onto the image, even if you don't know any regression, and you get these formulas. So it's really nothing special. It's just a special case of this, which is really coming from projecting y onto the image of this. Okay. Do it as an exercise for yourself, and that's like all for today. Thank you.